The last speaker of the conference is Matěj Kudrna from our institute. He will tell us about his research of marginal deformations in open string field.
Okay, so I would like to thank the organizer to allowing me to give a presentation here. First I have to apologize that I have COVID recently, so I hope that you'll be able to understand me because I have still a little bit of trouble talking. So I'll be talking about marginal deformation in open string field theory. Maybe I should look here so I can see it. So what is the reason why are we concerned with this topic? The reason is that there are many theories which have continuous spectrum of boundary states which have the same energy or G function. And as you know, the simplest example are Dbrands in a flat space where we can change their position or Wilson line, or if we can go to some more complicated theories. For example, there is a continuous spectrum of boundary states in the double Ising model or in Vesuminoidal models and so on. So if we look at such model from the perspective of boundary conformal field theory, then we find that such boundary states are related by deformation of the boundary action. Where is the pointer? Okay, so if this S0 is action of the original theory, then we can deform it by integral from a boundary field of weight 1 times some parameter which we call boundary marginal parameter, and this action should describe a different theory which have different boundary conditions. So such families of boundary states are related to existence of boundary fields of weight 1. So this is the process from the perspective of boundary theory, and I would like to describe this in terms of open string field theory. That should be possible because of the backgrounds of independence of open string field theory, which states that there is a one-to-one correspondence between open string field theory solutions and boundary states. And the results I will be presenting will be done in the level truncation approach in SIGO gauge, but I won't be going into any technical details. So in open string field theory, we parameterize solutions by coefficients in front of the marginal field. So the string field will be given by the marginal parameter lambda s. This is the first mode of the marginal field, and this is just the vacuum, plus there's the infinite tower of other states. Okay, so what's important here that the marginal deformation solution really doesn't depend on the background. So it doesn't really matter what's the theory, how many primaries we have, what are the conformities, and so on. And the solution really depends on properties of the marginal field J, or more specifically on its OP. So in this case, I will be considering marginal field which have such OPE that is a double fold. I will be discussing this in the free boson theory mainly, so I'll have put a factor of 2 here, but it's not so important because it just leads to some rescaling of this constant. So essentially when we are describing marginal deformations, we have two marginal parameters. One is this lambda s, which parameterizes the solutions, and we have lambda b, which parameterizes boundary states. And we should be able to relate these two parameters using gauge invariant observables, because these allow us to identify solutions as a boundary state, and for a given parameter lambda s, we can compute lambda b and determine the function between them. Gauge invariance observables of course depends on the background theory, because they essentially give us coefficients of the boundary state, and each theory has different primaries, so obviously the observables must be different. But when one tries to do these calculations in several different theories, one finds out that the relation is essentially the same. And since we are doing this numerically, essentially within numerical error, we find that for a given lambda s, we find always the same lambda b in many different theories. So in this talk, I will essentially present two different kinds of results. So first will be, as I said, the universal solution, which describes margin deformations of the perturbative vacuum, and I will be doing for the cosine X deformation in free boson theory. And I will discuss this solution in three different approaches. The first one is the perturbative approach, when we essentially expand the solution in lambda s for a small value of the marginal parameter. The second one is the marginal approach, which is the original approach by Sen and Zwiebach. And the third one will be the tachyon approach, when we parameterize the solution by the tachyon coefficient instead of the marginal field. So this part of the talk will mostly cover all the results, and this will be more or less a review with a bit improved analysis. And in the second part of the talk, I will describe margin deformations of solutions in the SU2-Vesuminov model. But in this case, I will talk about margin deformations of non-trivial solutions. So such solutions do not preserve the Dbrands energy, and they are non-universal, so only really depend on the model and on the solution we start with, and these will be new results from work in progress.
So excuse me, so marginal deformations, the exactly marginal deformations always preserve the Dbrand energy. So you are talking about non-exactly marginal deformations?
No, it's like marginal deformations of a solution will decrease the energy. So this essentially mean like combination of relevant and marginal deformation. You can essentially imagine that you take boundary theory, first deform it by relevant operator.
Which operator?
Relevant operator. This reduces the G function, and then this new theory, you deform it by marginal operator.
Okay, so yes.
Yeah,
so it should not be called marginal deformation because you first do relevant deformation and then you do marginal deformation.
Not okay. Well, it's like marginal deformations of a different background. Okay, maybe the terminology is not exactly correct here.
Okay, well, we'll see what you mean.
Yes. Yeah, so it's like it's preserve the energy, but different energy than the background. Okay, so here I have some references. So in the free boson part, I'll be using most of these references. So this is the original paper by Sen and Zwiebach, and these are some papers of me and my collaborators. In the second part of the talk, I will be using my paper about the Vesuminov model, and the rest will be a unpublished result. And here there are some more references about marginal deformations in open string field theory, both numerical and analytical. So first, I will quickly talk about the setting in the free boson case. So I will consider free boson theory on the pseudo radius r equal 1. And I will start with Neumann initial boundary conditions. So the reason I'm using this setting is that that's a relatively simple theory where everything is understood. We know exactly the boundary state. another nice thing that it has a higher symmetry. From U1, it's extended to SU2, and it's due to SU21 Wazumino-weighted model. Although I won't be really using this duality here. So since it's a simple model, I can do high-level calculations and get the results with good precision. Okay. So in this story, there are three margin operators. Essentially, what's important are the del-X marginal operator, which would lead to excitement of the ozone line, but I'll be doing the other one, which is cos-X marginal deformation, and such marginal deformation interpolates between Neumann and Dirichlet boundary conditions. So we get solutions that are actually very similar to lump solutions. Okay, so next let me quickly talk about the observables in the theory. So for the first one is obviously the energy, which is essentially given by the string field theory action. And the energy of solution is proportional to Dbrands mass or boundary state G function from the boundary theory point of view. And as it has been mentioned before, it should not depend on the marginal parameter. And the next observables which we have are Elwood invariants. They are parameterized by boundary bulk on-shell operators V. And the meaning of these invariants is that they should reproduce boundary state coefficients. So these invariants really enable us to identify open string field theory solution as a boundary state. So I'll be considering these invariants. They essentially include either some momentum or winding states or the del-X operator. You probably don't have to remember the exact definitions. They won't be important. What's more important that for this type of deformation, which I consider, that the expected values are given by some goniometric functions of the marginal parameter lambda b. So you can see it's either sine, cosine, sine squared, and so on. So I will start with the perturbative approach.
Sorry, I have a quick just notation question. What was psi sub TV?
Sorry?
This psi minus psi TV, what is the, oh.
Oh, yeah, this is the tachyon vacuum solution. And you can actually replace this piece by expected or the value of the boundary state coefficient for the initial boundary state.
Okay, and just a question about the previous slide is just very naive. You say you're going to interpolate between Neumann and Dirichlet boundary condition, right?
Right.
By turning on this cosine x. So it's like going from a D1 brane to a D0 brane?
Yes,
roughly.
exactly.
But their tensions are different, right? For the two branes?
Yeah, they are different in general, but the special case is because we are on the pseudo radius. So if you use specific normalization conventions, then you can say that energy of these boundary states on this radius is 1. But this can be done only on specific radii. I think that it can be also done on integer radii or maybe some rational radii between some different configurations.
So you're saying at this radius, the energy of the D1 brane and the D0 brane are the same?
Yes.
I see.
Yeah, that's I said that it's due to SU2 Wazumino-weighted model, so there's SU2 symmetry which allows that.
Okay, thanks.
Yeah, if you consider general radius, you will be able to do only cos-X marginal deformations.
So the psi say TV, I understand, but on the other side you have the E. What is the E there?
Oh, sorry?
The E that you have in the left, the bra.
Yeah. Oh, okay. Yeah, I didn't.
Okay.
Well, yeah. So this I didn't want to go to the details of the construction, but this is a Wood state, which is essentially the identity string field with insertion of this bulk operator at the point I. Yeah, this is the V. So this is the CC bar which to fill the ghost number. Here we have some primary operators, and the V is some auxiliary operator to give it a correct conformal weight. But yeah, in this case we have such operator. If you consider simple invariant like the X bar, this is already weight 1. So in this case, I don't have to do anything. So on this radius also we can have such mixed operators. We have del X and sin X because they have both weight 1. So there are some additional invariants.
Sorry, I wanted to ask, but in general, those invariants you consider here, where do they come from, or what is the D1? What is the H, for example?
These names are something which I have by myself, but they really come from bulk primary operators. So if you consider free boson, then the bulk primary operators are either some momentum states which are well, I have cosines, but you can have exponential of x or x tilde, or you have the exceptional primaries which are given either by del x or some higher weight primaries which has like weights 4, 9, and so on. Yeah, so these operators come really from classification of bulk primary states.
Okay.
Yeah, and this invariant should reproduce, as I said, boundary states components. Okay, so first I will start with the perturbative approach, because in some sense it's the simplest way to do. So for small value of the marginal parameter, we can expand the string field as a power series in the marginal parameter. We insert this expression into the equation of motion. The powers of lambda s are additive, so we can solve the equations order by order, and we get such a simple solution where the first term is given by the marginal field. Yeah, so this expression is analytic, and yeah, this B not over L not is like inversion of Q in the SIGO gauge. So in other gauge you can replace it by something else, but it's really general. Yeah, the difficult part is really evaluate the star product, because we have if you want to evaluate it, we have more and more star products, so it gets complicated, both numerically and analytically. So the main purpose of the solution is to determine the relation between the two marginal parameters, and we do it once again as a power series. So we expand lambda b as we write it as some polynomial in lambda s, where we have only odd powers because of the symmetry. Wow, so we expand the marginal parameter like this, and when we compute observables of the solution, so they also have the form of some polynomials in lambda s, and then we can take this expression, insert it into the expected values for the marginal fields, expand them, and we get such function, and we compare them, and this gives us some relations for the parameters AI.
Sorry, could you remind the definition of lambda b and lambda s? What's the difference?
Yeah, lambda s is coefficients of the marginal field, so it's string field theory parameter. And lambda b is some parameter which parameterizes deformations of the boundary state. Yeah, so I wrote it in the first equation when I have deformation of the boundary action, but in principle you can simply parameterize the boundary states by arbitrary parameter and say that this is lambda b.
Okay, thanks.
So here there are some actual results which you get. These are from level 22 solution, which was computed up to order 8. So it gives us the first 4 coefficients. So here you have some list of the invariants. And here are values for the coefficients. You can see that some of them are more precise, some of them are less precise. Yeah, but if you look at the arrows, you can essentially see that the values from the individual invariants agree with each other. So which means that the solution is consistent, and we can take like values from E1 or W1, which are most precise as the results. Yeah, this solution also tells us, since here you can see one without any errors, then in the first order, we can compute exactly that the marginal parameters are equal, and then there is some correction at the third order. Yeah, a similar calculation then can be Yeah, so I wanted to say that these coefficients can be calculated also in the marginal approach, although I won't be showing it, and we get almost the same results. So this actually shows that this solution should converge to the solution in the margin approach. Yeah, this will be problematic. So the perturbative solution has only a finite radius of convergence, which probably corresponds to length of the branch in the marginal approach I will talk about in few more slides. So in this case, I have computed two solutions up to order 400 at low level, and I compare gradual approximations of the solutions with the exact solution which are given by the points here, and this is the length of the marginal branch. So up to here, you can see that we can approximate the marginal solutions very well. After the end of the branch, the perturbative solution starts going widely up and down. So it suggests that really there is a relation between the radius of convergence and length of the branch. So we can actually try to compute the radius of convergence by taking this kind of limit where this Fn is expansion of arbitrary quantity. It can be either one of the gauge invariant observables or some coefficients of the string field. And we take the ratio and square root. The reason is that the reason I have n plus 2 here is that essentially our quantities are given by even or odd powers of lambda, so we need to have a difference of 2 here. So here in this plot are actually some results for these ratios at different levels. So I think that the red is level 3, so and this axis is approximately the radius or is the length of the branch. So at level 3, it really quickly converges to it. Green is level 4. You can see that there are a few jumps up and down, and then it goes it. Blue is level 5. So you see that it's more and more chaotic at the beginning. It oscillates and it converges. And at level C up to level 400, we can see just some random oscillations around the expected radius of convergence. Yeah, so that we see it at low levels, it converges to the right number, but it's not likely at higher levels. Yeah, considering that like the point when it starts to behave nicely, moves up in the order, suggests that maybe we need really high order to see the radius of convergence at higher levels.
Excuse me, I somehow missed what was plotted on the vertical axis in this picture.
Yeah, I plot the estimated radius of convergence by doing this kind of ratio between coefficients of expansion of some quantity. I think this is for one of the Elwood invariants, but I don't remember which one it was.
The radius of convergence of the sum in lambdas.
Yes.
Okay.
Yeah. Yeah. So it suggests that it has a finite radius of convergence. However, we probably need really high order to see it if we go to higher levels. Yeah, but there could be some issue of numerical errors if I go to such high orders. So I'm not exactly
Sorry,
Sure.
n is power of lambda, right?
Yes, n is power of lambda.
I have a question. It seems like you go back to the previous slide. It seems like the level 6 is just oscillating up and down about the correct value. If you plotted instead of plotting the ratio of the neighboring coefficient, what do you get if you plot the actual like log of each of the coordinates on like the log scale and like check the slope? What happens if you do that?
Logarithm of what?
Like logarithm of fn versus n. Like it seems like you would get something roughly linear with the right slope.
Oh, honestly, considering it's like jumps randomly, I don't think that you get anything reasonable. Yeah, if you look at the blue curve, it seems like something like some modulated. At least here is looks like some modulated sine or cosine. So maybe you could like imagine there is some sine which is quickly jumping up and down, and you are taking samples of it. But I'm not really sure what's happening. I didn't really find any kind of meaningful information of the level 6 data.
And, can you remind me what are the different colors of the points on the?
The different colors are levels. So this red, green, and blue are levels, I think, 3 to 5. So these ones seem to converge to the radius, and this blue one is level 6, and this one behaves badly.
So the green one is level 6.
I think green one is level 3 or 4.
I mean the light green. Light green, or what is it called? Like the many points that I see like above n equals 300. There are many green points. Or what is that? Or yellow or gray, or what color is that?
Yeah, well this one is supposed to be yellow, and this is level 6.
So all these chaotic points are level 6.
Yes, it was supposed to be yellow, but I think when I exported the image, it gotten some kind of strange color. Yeah. The others are clean. That they behave nicely around the axis, and these remaining are level 6, which are scattered around.
Yeah, like the reason I was like asking about this is because like, for example, if I consider like the function like 1 over z squared plus 100 times z over z 1 minus z squared, this would have, if you plotted that quantity, you would have oscillations forever, but it still has like a well-defined radius of convergence, because if you plot the lib soup, you still have a straight line. So that's why I was asking about it here, because it looks like when you have this convergence happening, this is somehow saying that it's even more than just convergent. It's literally there's one dominant contribution and just a single exponential.
Oh, yeah. So what did you say about the exponential?
I mean, so like, it's given that the ratio between neighboring terms is approaching a single value, it seems like it's even more than saying it's convergent. It's saying that these high order terms are just completely determined by a single contribution, which is like some exponential in n.
That seems too strange to me. I think that this is the usual way to compute the radius of convergence. Yeah, that's a bit different. I'm confused. I'm not comparing the neighborhood terms by what terms still by differing by number of 2, but I think that this is the usual way a convergent function should behave, right?
Yeah, like, but there's no need to have to stabilize. You don't have to stabilize. It just has to be bounded. In fact, I can actually have arbitrarily. I can make a convergence series. I can make a convergence series where like that thing has arbitrarily high values.
Yeah.
No, it does not have a finite. It does not need to have a finite limit. I can give you a counter example.
I think that the numbers are probably bounded. They are scattered around, but if they behave like the blue one, we can probably expect that after high enough order, they will get closer to the axis. But yeah, I don't have to prove that they are bounded, but I think that they should be. Okay, so next we'll go to the marginal approach, which is the original approach which was started by Sen and Sviba. So in this case, the solutions will be parameterized by coefficients of the marginal field, and for each value of the marginal field, we'll compute a solution. And since we set the marginal field to a given value, and we have one less dynamical variable, so we have to remove the corresponding equation. The solution is symmetric with respect to change of sign of lambda, so we can take lambda to be positive. Yes, and if you look at this model at the, I think this is level 1, you get this famous picture, and you have two branches of solution. Here is the marginal branch, which is connected to perturbative vacuum here, and here is the so-called vacuum branch, which is connected to tachyon vacuum, and it seems to be unphysical. So in this case, I was able to do numerical calculations up to level 18. So as you could see from the picture above, the branch has only a finite length, and it ends by meeting the vacuum branch. And if we consider higher value of the lambda s, then we find only complex solutions, which doesn't seem to become real. So we have a branch of solution, but there is no guarantee that it really describes marginal deformed boundary state. So but it happens at least at some part of the branch, because if you consider, like, let's say in some sense small value of lambda, then the observables agree with the expected values, and we can compute lambda b from various invariants, and they agree, and the equations of motions which yeah, and the equations of motion which are missing, which is either the equation for the marginal field or out of Siegel equation, so these are also satisfied quite well. But if we get towards the ends of the branch, then the solution loses precision and it probably becomes off-shell. So I'll illustrate this on actual plots of some invariants. So in the first plot, we have energy of the solution, which should measure like Dbrands mass or G functional boundary state. So the energy should be constant, and you can see that it happens for most of the length of the branch. So these different colors correspond to the different level of daytime. So you see that like from red at level 2 to violet at level 18, it improves. And here this black line is infinite level extrapolation, and this is even much better. So somewhere up to here, you can't really distinguish from the axis, but then it goes quickly up. So this suggests that there is a problem with the solution. Here there is some other invariant which should also measure the energy and behaves in a very similar way. So most of the time it goes along the axis, and this time it goes down from it. And here we have some invariants which depend non-trivial on the marginal parameter. So this should be something like minus sine of lambda, and this should be cosine lambda. Yeah, so for most of the length of the branch, it really defines like sine or cosine of some unknown function lambda b. But when we get here towards the end, you can see that the infinite level extrapolation goes below -1, and the same happens here. So this suggests that the solution is inconsistent, because no matter how we parameterize the function for the boundary marginal parameter, we can never go outside the allowed range. Yes. So here I essentially summarizes what I said before, that towards the end, the branch becomes off-shell. So the gauge invariants do not correspond to the expected boundary states, and we also check that it doesn't satisfy the out-of-Siegel equations or the equations for the marginal field. So it's inconsistent both as a open string field solution as a boundary state. What is slightly problematic is to determine where exactly it's supposed to end, because we can see that all the quantities gradually get less and less precise, but there's really no sharp change. So I'll try to answer this by going to the tachyon approach, which will give us some additional information. Okay, so this approach was introduced by me and Carlo in this paper, and the difference from the previous one is that we parameterized the marginal solutions not by value of the marginal field, by value of the zero momentum tachyon coefficient. So if we fix this coefficient, then the marginal parameter lambda s changes with level. And of course, we have to remove the corresponding equation, because once again, we have one less dynamical field. So in principle, since these two approaches should correspond to to one analytic solution, they should converge to the same solution in the infinite level limit, but of course at finite level they are different. And the advantage of the tachyon approach that it actually covers more of the moduli space. So in the first plot, in the first picture, I plot the dependence of the marginal. I plot dependence of the marginal coefficients on the tachyon coefficient. So the I think general shape goes like this. It goes like something like this is 1 over square root, I think. No. Oh. Yes, yeah, something like that. But the important point is that it has a maximum somewhere, and it starts going down. And since we parameterize the marginal solution by value of the marginal field, and it's obvious that in this region we cannot reproduce this tachyon approach just by one branch of solutions in the marginal approach. So like this second half of the branch should be reproduced by a different branch in the marginal approach, but we haven't able to find it for some reason. So once again, I will plot some invariants. So in this case, we have once again the energy. And like in the margin approach, we see that it gets gradually less and less precise. In this case, you should notice the scale, because in the margin approach, like I was showing like this region, and in this case, we have several times the expected value. So really, the infinite level extrapolation down here is really not very precise. Yeah. So this suggests that the solution also become inconsistent somewhat towards the end, but it's even less clear where it goes off shell, because the loss of precision is more gradual. Okay, here I have some invariants, which depends on the marginal parameter. So in this case of this E invariant, it behaves something like minus sign. So it goes to 0, and then it goes up, and in this case, there's this dashed line, which denotes some kinds of fate of the boundary marginal parameter, and then then I computed the expected value using the fate. You can see that we can approximate it very well. But in this case, we have different invariants, which is called W1. In this case, we can see once again that it goes below be a range which could yeah, so it goes below -1, which is the limit for finite cosine, so we can kind of guess that it goes off shell somewhere around here, but since we are not exactly sure about the precision, we cannot say precisely where it goes off shell. Yeah, but a nice thing about this approach is that we can really get a good estimate where the solution describe the Dirichlet boundary conditions. If I go back one slide, so we have a minimum. We can approximate this function by some polynomial and compute exact position of the minimum. We can get this value of the marginal parameter. So in this line I have some other way to compute this position of the Dirichlet point, which comes from some extrapolation of lump solutions, and you can see that there is a real very good agreement with these two numbers.
Beginning that the marginal deformations are in some sense universal, so it's the same calculation that determines the lambda S critical.
What do you mean by critical here?
No, I mean
end of the branch or the Dirichlet point?
Sorry, it's the branch of the.
Yeah,
it's some critical value of lambda S, right?
Well, you have essentially two critical values. One of our special values. One of them is the Dirichlet point, so where it describes Dirichlet boundary conditions, or maybe you could have three. Next is where it go off shell, and third is length of the marginal branch. So.
Oh, I see.
So which are one of these two mean?
Oh, I meant the branch, but you are doing the Dirichlet point, right?
Yes. So this point really is where the solution describes Dirichlet boundary conditions. Well, kind of. Yeah. If I go a few slides back, maybe
it's like 10% away from the branch point, so on the right side, the correct side.
Yeah. Okay. So here I have plot of the marginal branch again. And here you can see the infinite level extrapolation goes towards -1, but it crosses it. So you should do minimum here. So it kind of covers this point, but it becomes imprecise. So yeah, so I'll talk a bit about it later. Where I was. Okay, here.
So what's the reason that the lambda S Dirichlet should have the same value from two different solutions? Why it's 3752 in one approach and 3751 in the other approach?
No, this is a completely different estimate. This comes from lump solutions and different radii and extrapolation to R = 1. So this is completely different approach, which wasn't done using marginal solutions.
But it's using the same CFT.
Yes, but everything has finite precision. So. Yeah, so I think that since it differs only like at this digit, so I think that that's pretty good agreement. In case of the tachyon field, the agreement is slightly worse, but I think that in this case, this number is actually larger error for some reason. So let me go once again back to this plot. So here I have said that we cover Dirichlet boundary conditions. But since it's go up and goes through 0 again, so it's possible it can cover also once again Neumann boundary conditions, but this time there will be Neumann boundary conditions with different value of the Wilson line. And here is some estimate what is the lambda S from the Neumann boundary conditions, but at this point it's not entirely clear whether the solution is still on shell. Okay, well, I'm going much slower than I expected. Yeah, so then I'll be going back to marginal approach and to use the information from the tachyon approach. Yeah, so as I said, we had estimates from the Dirichlet point, but what's important that we have also estimates for the maximum value of the marginal field, which was from the plot of the dependence on the marginal field on the tachyon field. So and this point should give us the maximum length of the marginal branch. So I guess this value should give us really the point where it goes off shell. And we can see that this value is higher than this one, so we should be able to cover the Dirichlet boundary conditions by this approach. Yeah, so in this plot, we have once again plot one of the invariants, and this line should determine the Dirichlet boundary condition. This one should be the end of the branch when it goes off shell. Yeah, but the unclear thing is behavior in this area, because the expected behavior according to the tachyon approach that it should have minimum here and it should go up, but it doesn't do so. So it's unclear whether the solution goes off shell a bit earlier or the precision of the level truncation approach in this area is low. Yeah. Here I will try another thing, and that is to determine where the branch goes on shell just from the margin approach data using error estimates of extrapolations. So when I do extrapolations, I can estimate errors, but they are not very reliable. So I can say something like the solution is wrong if some quantities where the errors is more than 3 sigma. But I can consider this kind of ratio. This is the actual error, and this is the error estimate, and plot it as a function of lambda. So here that it is for several quantities. I think that they are the energies out of Sigo equation and some other invariants. So you can see that in this area, yeah, this ratio of the errors is more or less essentially constant. You can see that the values are high. So this is like 15 sigma, which would be normally wrong, but I don't really care much. But what's important that around here, they start behave the same and they go quickly up. And this line is when the estimates from the tachyon approach where it goes off shell. So you can see that this kind of this ratio errors gives us pretty good estimate where the branch should end. And I'll be using this for the Wezon innovative solution later. Okay, I think that one of the final things about the free boson about the free boson approach is that I'll be talking about the relation of the marginal parameters. So in this plot, you can see the relation for one of the analytic solutions from this paper. So this T here is some gauge parameter. So and there are different lines. So the relation depends on gauge. It's linear for small lambda, then it has a maximum, and then it goes to 0 for large lambda. Yeah, the question is whether the numerical approach gives us something similar. So, yeah. So as you saw before, we have several invariants which depend on lambda. So we can compute it, we can invert the expected values, and using this function, we compute lambda, and we should get the similar values from all invariants, which essentially happens while the solution is on shell. So in this plot, here the red color is from the margin approach, and the blue one is from the tachyon approach. And you see that they agree very well up to end of the marginal branch. And for the tachyon, we can see there's a maximum, and then it goes down. So it's actually quite similar for what we saw for this analytic solution. It goes up, maximum, and then goes down. Yeah, and the final thing that I will briefly discuss is complex margin deformation. Yeah, what I mentioned, what I discussed so far were solutions for a real lambda, but in principle, there is no reason why we, we can't choose it to be complex. In this case, it won't have interpretation in the free boson theory, but it would have interpretation like in SU21, SL21 resuming Overton model, which is non-unitary theory. So if we choose complex marginal parameter, we get generic complex solution, but in most cases we have almost real action, which is supposed to become real in the infinite level limit. And such solutions are generally well behaved even outside the radius of convergence of the perturbative solution. Yeah. Yeah, and these complex margin deformations are especially nice for imaginary value of the marginal parameter, because then the solution has real action and is plot of the energy, and you can see that the branch is much longer. So the length of the marginal branch was like this, and here you can see that we are 4 times longer, and the infinite level extrapolation is still very precise. In this case, it's interesting like that the even levels, the energy goes up, and for odd levels, it goes down, but still, if you extrapolate, it is very nice. Yes, pure imaginary lambda. Yeah, and the action in this case is exactly real. Yeah, but I won't be showing the invariance here, but if you replace lambda by imaginary value, then the goniometric function becomes hypergeometric function, so the invariance go exponentially up or down. And here there's like some plot of what happens in a complex plane. So this red circle is like the radius of convergence of the perturbative solution. This red arrow would like, this is the range of the real solution. If we go in some complex direction, then we find solution even much longer outside the range of convergence, and generally we can find good solution pretty much everywhere here. Yeah, so the problematic part is the real axis. So what we can try to do is start here and go around contour like this. And in this case, we find that we don't return to the same solution, but we have to go around the circle either 2 or 4 times to get to the same solution, which suggests that there is really a branch cut along part of the real axis. Yeah, so this is kind of the structure of the solution for generic complex lambda. The existence of the branch cut is kind of expected, because for the real solution, we had only finite range of lambda s. So when we try to invert such function, we get some kind of square root, which leads to branch cut. Okay, yeah, so this is the end of the first part. So, and
sorry, naive question. On the previous slide, you have this branch cut. Would you speculate that it's lifted if you include quantum corrections? I'm guessing you're studying the purely classical theory. Or does that question even make sense?
Honestly, I have no idea.
Okay. And just another question for these complex values of lambda, I guess, or even the real values that are not Neumann or Dirichlet, do we understand the low energy effective field theory of the theory on the brain, on the boundary condition?
I think that the only way you can understand is to take SL2C Wezominowitton model. Yeah, because it has no meaning for the free boson, like what is Dbrands complex position. That doesn't make sense. But if you go to this non-unitary model, then I think that you could understand in terms of some blowing condition for the currents.
I think to your question, you also ask about the meaning of real lambda outside of the Dirichlet point. So in some dual picture, it just corresponds to Dbrand moving on like a D0 brand moving on a circle.
Can you explain a little bit more why you say, okay, so it seems you say that when you move along the possible branch point, you sometimes need to do four turns to come back to the same solution.
Yes.
But somehow this picture of a lambda string field theory having a maximum and then decaying suggests that you should just have like an order 2 branch point, right? So why? Because I mean, I mean that's like quadratic, right? There. So
yeah, I haven't thought about that. Yeah, I didn't study such a detail, so it may actually depend on the path, or it could be some numerical issue. Yeah, so the intermediate point you encounter here, either the vacuum branch or some complex solution. So
I see.
I'm not sure whether you can understand it, but I haven't thought about what you asked, so I don't know.
But is there some of this solution that you find? I mean, for example, if you do just one turn, you come back, then you will find some configuration that is different from the starting one. Is this a solution, or is it something that will be off shell?
Well, you get either the vacuum branch, which is considered to be on shell, or some complex solutions, which probably doesn't have a meaning.
Oh, I see. So you're not finding this extra branch that one would expect that should cover the region that is covering the Tachyon approach.
Unfortunately, no. Okay, yeah. So in this second part of the talk, I'll be talking about the SFT2022 model. And I already used most of my time, so probably I will skip this first slide very quickly. Yeah, so in this first slide, I have some summary of properties of the model. So as you know, we have these 3 currents, and the SU2 elements can be parameterized by 3 angle, and this is one of the possible parameterizations. Okay, here we have some property of the fields and currents. So let me just say that the primary fields are labeled by SU2 representations by the quantum numbers J and M, and this J is restricted by level of the Wezumino-Witten model. Okay, so in this model, we find 2 types of boundary states. We have either maximal symmetric boundary states, which preserve 1/2 of the bulk symmetry, or symmetry breaking boundary states which don't have this symmetry. And I will be focusing on the maximal symmetric boundary states. So such states satisfy this kind of gluing condition that we have left and right current, and here is some matrix omega, which is parameterized by SU2 element G, and this is something like adjoint representations. Yeah, so these conditions are solved by Ishibashi states, and we can use them to construct Cardi boundary states. So this is almost the same as in the minimal model. So we have boundary state coefficients which are given by the S matrix, and here we have the Ishibashi states which are labeled by J and group elements, and the boundary states are also labeled by groups elements and half integer. Yes. So when we actually do calculations in this model, we impose this condition on the string field to fix some residual symmetry, and this actually simplifies the whole problem quite a lot, because it implies that the solutions preserve a condition for the J3 current, which means that out of the 3 angles that parameterize SU2 element, only one of them survives, and we can write the SU2 element just like this, which is very simple. This model, I once again consider a root invariant. So in this case, they will be given by the SU2 primaries. So since this is bulk operator, it has 2 indices which essentially give the spin projection, but due to this condition, the labels are have opposite values, so I have just one index here, and then we have some invariants parameterized by the currents, but possibly out of 9 invariants, only 3 of them are non-zero. Okay, so when we extract the boundary state components, we find that the expected values are given by the matrix of the boundary state coefficients, which is this, and a complex phase given by the angle theta. And here for the other invariants, it's similar, and this one should be constant. Next, let me quickly mention interpretation of the Dbrands in this model. So the SU2 manifold is isomorphic to 3-sphere, and the Dbrands correspond either to points which are 0 branes, or the two spheres which are 2 spheres which are on the 3-sphere, which is for Dbrands with other values of the parameter j. Yeah, and this condition essentially fixes rotations of the sphere, so we can actually depict everything just on a circle. Yeah. So next I will mention the main results from this paper for the Cardi solutions. So we find many solutions that describe Cardi branes, but out of the possible infinite number of solutions which should form continuous families, we find only finite number. And the solutions which we find follow some selection rules, which says that this angle is related to difference between initial and final value of this parameter, which can be shifted by some integer. And if we plot it, so this black line is the initial Dbrand, and the solution which we find are given on such a lattice. So we have such points and lines connected, which would be some higher brane. And most of the solutions which we find actually touch the initial one at one point, and these are more precise, and the other one are less precise, and they are more difficult to find. So most of the results are represented here would be for K=2 model, where I choose J equal 1/2 boundary condition. So the picture is simple. We have a circle, and this is the initial Dbrand. And in the usual approach, we find just 2 solutions, which is not much out of the whole circle. So how do we cover rest of the moduli space? So we actually take inspiration from the Marginal Approach, and we look for solutions which are parameterized by the margin of field, but will be connected to this non-trivial solutions. So there will be something analogous to the vacuum branch. Okay. So in the Wasowino-Witter model, we have 3 marginal fields, but since we apply this condition, only one of them survives. It's given by this J-1,3 operator. So once again, what we do is we fix of the value of the marginal field, and with the corresponding equations, and solve the string field theory equations. Yeah, so if we do this, we would also once again find the marginal solution which I presented before, but we also find different branch of solutions which are connected to some non-trivial solutions which describe Dbrands with low energy. So in this case, these are 0 brane. Yeah. To parameterize these solutions, we divide this angle theta in some basic value, which corresponds to the initial solution, and by the rest, which I will be calling the boundary Manchuru parameter. You can add some constant like pi here, but I won't be doing this here. When we want to extract the marginal parameter lambda b from the invariants, what we can do is try either compute it from real and imaginary paths, since we have a complex phase, but this doesn't give very good results. So it's better to it's better to divide the values of the invariance into absolute values and complex phase, and just compute lambda b from the argument from the complex phase. So we compute argument of the invariance, there is some sign, and subtract the initial value, and this gives us lambda b. Okay, so here I will be talking here about the actual results for the zero-Dbrands solution. Yeah, so what we will be seeing is something very similar what we saw in the marginal approach. Yeah, the precision of the results will be lower because we are in more complicated theory, and therefore I can go to lower level. I think I was able to get like levels 10 to 12 instead of 18. Yeah, so there is a branch connected to the basic solution. It has a finite length. In this case, it's approximately 0.33, but it depends a bit on the level. It's symmetric with respect to change of sign of lambda, so we can consider lambda to be positive. And once again, for small lambda, it consistently describes different boundary state. Yeah, there's some issue for low precision at small lambda, but I will skip that. Yeah, and for the large lambda, it once again becomes inconsistent and goes off-shape. Yeah, so here there are some plots to illustrate that. So here is the energy. So once again, for small lambda, it's nice, and it goes down the axis, and it goes up. Yeah, so I said the length of the branch is like 0.33, so it will be somewhere around here. But you can see that it loses precision much before, and only about half of the length or the branch could be on shell, and there is even no point to analyze the endpoint. Here on the other plot, we have the first out of zero equation. You can see once again for high lambda, it's not satisfied at all. Okay, here is one invariant which depends on lambda. So this is E1/2, and it should be equal to some constant times e to the I theta. So in this case, you can see absolute value of the invariant, which should be once again constant, and behaves pretty much like the energy. It's constant for a while, and it goes down. In these two plots, you can see a real and imaginary part. So once again, this should be something like minus sign, and this should be cosine. And here, the black one is infinite level extrapolation, and this dashed line is the expected behavior, which is based on some kind of fit of the function for lambda b. Yeah, and now although we can fit the phase correctly due to the wrong absolute value, once again doesn't agree in this region. So in this model, we have three invariants which depend on the angle, and therefore we get three values of the marginal parameters on the three invariants. So here in this, I have example for this value of lambda, and these are the three values of lambda b which I get from three invariants. And you can see that they agree quite well. In this case, there is just difference of the last digit. This one is less precise, but that's kind of expected because it oscillates quite a lot. And here is actually a plot of the dependence of the two marginal parameters. And there are three curves. You can see up to, let's say, up to somewhere here, they agree quite well. And then each of them goes in a different direction, which suggests inconsistency of the solution. Yeah, so we can use this. We can use this and also this ratio of the sigmas, which I introduced before for the free boson solution, which is plotted here. And we can use this to estimate where the branch goes off shell. It won't be exact number, but we can get to pretty decent estimate. Yeah, so estimated this number, which are around 0.1. Yeah, it may be a bit up or down, but the error probably won't be much larger than this. Yeah, so now we know how much of the branch of this is on shell, but the question is how much of the moduli space is actually covered. Then we find out that the maximum value of lambda b is around 1. The value should be at least pi over 2 to cover the moduli space. So if I actually plot it, it looks like this. We will have the basic solutions and we cover approximately this part of the moduli space. Yeah, so it's like something like 60% of the range of theta. And if we compute the actual volume of the SU2 sphere, then it would be like 90%. Yes. So in this case, we have unfortunately cover only part of the moduli space, but we are able to find continuous familial solutions, which covers at least part of it. Yeah. Next, let me quickly mention what happens if we go to models which are K and different boundary conditions. So in most cases, we get similar types of solutions. Yeah, but one interesting issue is that some solutions are only partially symmetric with respect to change of sign of lambda. So these are two invariants for K equals 3 solution, or let's to be less precise, zero brain solution in K equals 3 model. So on the right, we have some invariant which is nicely symmetric with respect to 0. But on the left, there is a different invariant, and this is a generic function. Yeah, but when we compute the boundary Manchin parameter lambda b, and we find that this function is approximately symmetric, but we expect that it will become symmetric in the infinite level limit, and the length of the branch in both directions also should be the same. Yeah. Okay, so here are plot coverage of the moduli space in K equals 3 and K equals 4 models. So this is the case for the plots before. Here we have the asymmetric initial configuration because the initial Dbrands is not in the middle, so the solution is not exactly symmetric, and we cover this part of moduli space. You can see that we can cover most of the top, but very little of the bottom of the circle. Yeah. And on the right, we have K equal 4 model. So in this case, we have actually 4 seed solutions. Yeah, so for this one, we cover this part of moduli space. In this case, the solution actually has a bad precision, so I was not able to determine exactly what is the maximum value of lambda b, but schematically it covers a part of moduli space like this, but I'm not sure about the exact length here. Yeah, so in this slide, I've just the summary of what I said before. So let me skip that because I'm over time. Yeah, and towards the end, I would like to compare the values of lambda b, which are get from different solutions because there are some similarities. Yeah, so I will compare actually this function where I have added the square root of k to compensate for normalization of the marginal field. Okay, and here's the plot, and you can see that there are many solutions or several solutions for which this function is similar. Yeah, so let me go quickly what we can see here. So red, green, and blue curves are zero brands in K equal 2, 3, and 4 models. Yeah, you can see that all of them behave similarly. Of course, yeah, these are some fits, so the solutions go off-share somewhere. So the endpoint is end of the curves is not relevant, but in the beginning they agree quite well. This yellow one. Is this solution which has real bad precision? Yeah, so it kind of stays similarly, but then it's different, and I'm not exactly sure whether it agrees with the others or not because of its lower precision. And this magenta line is for 1/2 brain, and you can see in this case it's clearly completely different. Half brain is a brain with J equal 1/2. So I think that this is in a K equal 4 model where I stated from J equal 1, and this is J equal 1/2 solution. And these others are J equal 0. Yes. Okay. Yes. This plot suggests that all these solutions, although there are no different backgrounds, they may have the same first coefficient in the expansion of lambda, and possibly they could share even the whole function, but we can't really say that with this precision. Oh, yeah. I would say that it's, well, my conjecture is that there are several classes of solutions and each of them would have similar function or at least some coefficients. Yeah, it could be like zero brains has one function, one half brains have another function, and some other solutions could have some completely different function. Yeah, and there is a one more line which should be orange, although it looks kind of brown, and this is for B brain, which is a symmetric breaking boundary state, which I will quickly talk about in the last two slides. Yeah, yeah. Yeah, so how do I use this approach for the Dbrands? It can be also used for symmetric breaking boundary states. We can try to define them in the same way. So I have done it for Dbrand in K equals 3 model, which has once again some parameter j equals 0. Yeah, so there are some slight differences. In this case, it seems that the whole branch is on shell. Yeah. In this case, the solution of the boundary stage is much simpler because most of the invariants should be equal to 0, or at least they should be constant, and there is only one invariant. This is this E3 halves, which depends non-trivial on the marginal parameter. And here I have some plots of the real and imaginary part of this invariant. So once again, we find that its absolute value is almost constant, but its complex phases changes. So we can guess that it behaves similarly like for the Dbrands like this. We have some absolute value and then we have a complex phase. Yeah, so what's interesting that there is some coefficient, and if we choose this coefficient to be 3 halves, it should be probably, which is obviously related to this label of the invariant. And if we do this, then the boundary margin parameter also agrees with the 0 brain. So there is a possibility that this B brain solution actually shares the same function as the 0 brains. Although I don't really have exact interpretation of the boundary margin parameters for the symmetric breaking boundary states, but the numerical results suggest that there could be a relation. Okay, yeah, this will be an end of my talk. So are there any further questions?
Oh, actually, I was looking for the microphone.
I have a question. So do you think you can apply some of these techniques to open superstring field theory?
Oh, you mean like this deformation, like margin deformations in general, or this?
Yeah, or in general, or in some nice backgrounds. I don't know.
Well, I suppose it should be doable as long as you are able to construct the string vertices. Yeah, so.
Yeah, so I think that at least this Wezumino-Witten theory by Nathan Berkowitz is based on Witten star product. So
Yeah, I
Should
think
not be
it,
that
it should be
different.
probably doable, but it will be probably very difficult numerically, so you probably won't be able to go to high level. But I think in principle, yes. Yeah,
What would be so difficult about it? Okay, I mean, maybe there's some more fields, and okay, maybe you have to compute a
yeah,
few
if,
more
if I remember
products.
correctly, I saw some calculation and included like higher vertices, so which have worse scaling of the required time with the number of fields. So I think that this will pose a problem, like how far you can get, but in principle it's doable.
Yeah, I mean, basically, since the early 2000s, there's been no level truncation computations in superstring field theory. So I think you can't really say whether you can do it or not because nobody's really tried that hard.
Yeah, I think it should be doable principle, but I've never even tried. So
yeah. Yeah, but it's, the vertices. I mean, if you know how to compute star products, then it should not be a difficulty.
Yeah, you would probably need some combination of level truncation and order truncation and combine it together in some meaningful way.
Well, I think for the Berkovitz theory, I think you know how to how this goes because you only at a finite level you only need a finite number of the vertices. So if you only include the tachyon, you only need, I guess, the quartic vertex, and the other vertices are just 0. And so I think that issue is only really a problem if you have vertices that are integrating, or you need to integrate over some portion of the bosonic moduli space. So for the Witten type vertices, I would guess that you don't have this kind of ambiguity that you have for these kind of questions that you have for the closed bosonic string field theory, for example. So if you want to compute the tachyon potential at level 0, there are a finite number of you only need the quartic vertex. You don't need to compute all the other vertices vanish by some twist symmetry or something. No, I don't.
Yeah, that will simplify, but the question is
Yes.
what happens for higher fields? Because I suppose with the number of vertices you need grows quickly as you go up in level.
I don't know if Ashok is listening, but he may. I think it's possible to do these kind of calculations, but I don't remember the details. You only need a
I think it should be possible. It may be a little more complicated. Yeah, but I don't see any real difficulty.
But there should be only a finite number of vertices you need if you're truncating to finite level. Is that correct? No, I don't.
Exactly.
Remember.
Yeah, I think so. Yeah. As far as I remember, that's the case.
Yes.
Yeah, so if that is true, that would be a simplification and it would really give you some meaningful truncation you could try.
Yes, I think that's worth doing. Yes. Okay. Yes.
Question. So what do we know about, in general, about the relation between lambda B and lambda S? So what are the details of conformal field theory or the boundary conformal field theory on which this relation depends, or to which level it's universal? So I understand that the first coefficient is 1, which is universal, but how do the other coefficients depend on the BCFT?
But the solution itself, if we go to the solution connected to the perturbative vacuum, that is universal because it's constructed only using the marginal field. So the relation between the two parameters should not depend on the model, but it depends on the gauge which you choose. So in SIGO gauge, it's going to be different than for some analytic solution.
So the relation between lambda B and lambda S doesn't depend on anything? Only on the gauge? It doesn't depend on the BCFT details?
No, if yeah, I probably don't need to go to the first part of the talk when yeah, but yeah, if you have a really basic solution which is connected to the perturbative vacuum and not this solution which I used in the Vesumino-Witten model, then it really depends on OP of the current which itself. Yeah, you can understand it from the perturbative solution, which is written as a series where the individual terms are given by star products, which and the first term is just the marginal field. And the higher terms are product of the marginal field with itself and more star products, but it starts from the same state, so it doesn't really depend on the model. Yeah, the only thing that you can change is like normalization of the field, which is trivial, or you could possibly use a current with different OPE. So if you if you have, for example, current without a pole, then the solution would be probably different because you would have different OPE. Yeah, but if you fix the OPE, then the solution should be always the same, and the relation between marginal parameters too, maybe up to some redefinitions.
Yeah, okay, because the coefficients of the boundary state, for that you need the correlation functions of one bulk operator and the arbitrary number of boundary operators. And this quantity seems to depend on the detail of BCFT or not.
Yeah, I said it at the beginning that that the invariance of course depend on the boundary CFT, but it seems that the relation between the marginal parameters does not.
So these marginal currents, they are universal in the sense they have this double pole, then nothing, and then they have finite contributions. But I imagine that the finite contributions to the OPE will in general depend on the CFT you are using. And so doing the star product of J's won't give you the same results in any CFT, or yes. I mean, I don't know, but it would be, to me, okay. So.
Yeah, I think if you if you do the star product, it should be the same for all currents, right?
I don't know. This should be something known in CFT, whether the OPE of two marginal currents is in every CFT.
Yeah, I have a vague recollection that for spin one or integer spin operators, the correlation functions are pretty uniquely fixed.
I think that the correlations are fixed by the divergent part of the OPE, and the finite terms do not contribute, right? If I remember correctly.
But I mean, the finite term will surely contribute to the star product, right? Because the star product is given by the finite distance OPE. The question is whether these finite contributions are essentially the same in every CFT or not, and probably they are for exactly marginal current, but I don't know. I mean,
it seems hard.
I think the only. Can I just add something? I think the only operators which will appear in the OPE are the descendants, the current algebra descendants of the identity, right? I think those should be universal.
Yeah, it's possible, for example, that the finite part is given by the energy momentum tensor, and
but I think that's still by Sugawara construction JJ, right? I mean, it's
yes. So I think that you have the same center charge for the energy momentum tensor, so it's just wait one current, so the central charge is going to be 1 for this part of the CFT, and this may determine some finite part of the correlations that could be the solution.
Yeah, because I would think that if you take say the a correlation function with some j's inserted and one primary, which one non-trivial primary of the current algebra, the correlation function will be 0. Right? Because using the j's, you can convert back to the just the one-point function of the primary.
Right. Yes.
So this part is universal. What I'm not so sure is the lambda b. I mean, how universal is the definition of lambda b? In the BCFT, I mean, is there a way to, I mean, there will be divergences, right, from collision of vertex operators, and you have to somehow normalize it.
I think
is there a universal?
Yeah, so
procedure?
Nagel and Schomerus gave a way to define lambda b essentially by doing this sort of regularization of boundary interaction or integration. But I think regularization they used was only valid for a specific class of marginal deformations that are these self-local marginal deformations. And I don't know if there is
I'm not sure whether there is some analytic proof that the relation is the same, but when I tried it numerically in several different models, like the free boson, I tried doubleizing this Wezumino-Witten models. In all cases, when you choose the same lambda s, you get pretty much the same lambda b within some pretty good precision. So I think that this suggests that the relation should be always the same.
I don't know how generally we were discussing the 3-point function, but if you just have a general CFT, not like a Wezumino-Witten model, then it seems like the JJ and some spin O 3-point function is some generic thing that's not just fixed by the OPE of J and J. As these WZW models may be more special, but I mean, conformal invariance wouldn't restrict that.
Oh.
Yeah.
You mean to J's and some other?
Yeah. Because that's what appears on the right-hand side, right, of J. Sorry?
Function. So two marginal currents and any other state of spin 1, I mean of weight 1, will be 0 by exact marginality.
Yeah, but if you compute like some out invariance, then and you would put some bulk fields, and in this case, this could be non-zero.
Yeah, but because this is like
yeah, but that is a different thing.
Yeah.
Yes, of course.
Right, but the Elwood invariant, these are two bulk. This chirally is two fields. So
yeah, well, it's one bulk and
yes,
number of boundary operators.
Yes, so
but
this is not fixed.
In the matter sector, all of them are dimension 1, right?
Yes.
So I wonder whether that is fixed.
I don't think this is fixed, because I mean, otherwise, I mean, all string theory backgrounds would look the same somehow. I don't know. I mean, there should be some difference, right?
No, this cannot be fixed. Yeah, what is fixed of coordinate dependence, but it's given by some generic structure constant, which depends on the theory.
Yeah. I mean, fixed up to maybe some overall constant.
Yeah, but this overall constant is the structure constant, which determines the theory. So.
Which structure constant?
Well,
the bulk boundary.
Bulk boundary structure constants.
Well, I think we should thank also our streaming participants for having a really nice and meaningful presence in our meeting, and we really value their comments. So unfortunately, the discussion session is never streamed, so we say goodbye to all the streaming participants and hope to see you in person on the next meeting some near future.
Okay, thank you.